All right, well then I guess we'll go with my original plan to go over the practice questions. So the first one says, draw a correct structure corresponding to the following compound: 1,2,3,3 tetramethyl 1-cyclohexene. Well, remember that by definition, with a cycloalkene, the double bond is between carbons 1 and 2. Actually, that's not going to work. I have to put them inside, otherwise I won't be able to put my methyls on. So then we just need to put 4 methyl groups on in positions 1, 2, 3, and 3. 1, 2, 3, and 3. So something like that. Honestly, I'm not even sure you need to say 1-cyclohexene. I think 1,2,3,3 tetramethyl cyclohexene might almost be okay, because the double bond is assumed to be starting at carbon 1 with cycloalkenes. So something like that is what I was looking for. In the reaction of compound A, styrene with hydrobromic acid, 2 mechanistic outcomes are possible, resulting in both compounds B and C being potentially formed as products. So this is something we couldn't do in chapter 6, but we can do in chapter 7. Because in chapter 7, we learned about Markovnikov's rule, which says that you're going to go through the more stable of 2 or more possible carbocations, whatever is the most stable carbocation. And we have a choice of putting the plus charge on this carbon or on this carbon. Let me highlight them a little better. On that carbon or on that carbon. And it's much better to put the plus charge on this carbon because it's secondary as opposed to primary. And also that carbon is benzylic, which means you get an especially stable carbocation for being only secondary. So that means the bromide is going to attack over here, and compound B will be preferred over compound C. Compound A isn't even a product. So that's what I was looking for. And I think that's it for that page. Well, what the heck? Since I have a feeling we're going to have all kinds of time, let's review that mechanism by which we get compound B. This is a mechanism we've known since chapter 6, so hopefully it's very familiar. In the first step, double bond swings out to pick up the proton from HCl, HBr, or HI. We break the hydrogen-halogen bond. And we're left with a carbocation, like that. This carbon now is a CH3. It started at life as a CH2, but it gained another hydrogen from the HBr. And of course, this carbon still has a hydrogen on it too. It's a secondary carbocation. And then bromide ion attacks. think I missed. That's a little better. And you wind up with the halogen over here. So much for that. Next, we have an energy diagram question. This comes from today's material in chapter 7 on the Hammond postulate. And also previous knowledge about energy diagrams. So first of all, it's asking about the transition state TS1. And it's asking what species that looks the most like. So remember what Hammond's postulate says. It says that for any transition state, what you need to look at is the two species that are immediately surrounding that transition state. So you've got the starting material and you've got this intermediate. And it says that whichever of those two species is closer to the transition state in energy is the one that the transition state looks more like. So this transition state is closer to the intermediate than it is to the starting material. So transition state 1 is more like the intermediate than like either the product or the starting material. And then it says transition state 2 looks most like which of those? TS2 is up here. It's between the intermediate and the product. Hammond's postulate says that whichever species that one is the closer to is going to be the one it looks more like. So transition state 2 is closer to the intermediate than to the product. That means it looks more like the intermediate than either the starting material or the product. But remember, you always need to look at the transition state and find the two species that are immediately surrounding it. That's what you need to look at when you're asked about Hammond's postulate. And I don't think I can state it more simply than that. How many steps are in the reaction? Well, remember that there are as many steps as transition states. So this is one step going through the first transition state. This is a second step going through the second transition state. In fact, this energy diagram could be for the addition of HCl, HBr, or HI across an alkene. So it is 2 steps, since there's 2 transition states. And that's pretty much it. I could have asked, is the reaction overall exothermic or exergonic or endergonic? And since the product is lower in energy than the starting material, the overall reaction is exergonic. The first step is endergonic, and the second step is exergonic. So I could very easily have asked them about that also that year. And if you have any questions, there's only 2 of you, so feel free to just interrupt me.
Sounds good.
All right. This is a question about an E2 reaction. And our goal is to make this compound, this alkene, from this starting material. So you can already identify the carbon that has the leaving group on it. And we're going to eliminate HBr across these 2 carbons and make a double bond there. We're going to do it by an E2 reaction. So the first question says, provide an appropriate reagent and solvent to direct the reaction to the E2 product rather than one of the competing reactions. So to do an E2 reaction, we need a strong base, and pretty much any strong base will do. Sodium or potassium hydroxide, sodium ethoxide, sodium methoxide, potassium terbutoxide, any of those would be fine. And to pick a solvent, if we really wanted to make absolutely certain that it goes through an E2 reaction, we can use a polar aprotic solvent like DMSO. And be sure you know the structure of DMSO. I don't want you guys just memorizing alphabet soup names. I want it to mean something to you. I could ask you, what's the structure of DMSO? Absolutely, that's fair game for this exam.
And what type of solvent did you say it was?
Polar aprotic. Favors SN2 and E2. You can't get a carbocation in a polar aprotic solvent. So you're not going to get an SN1 or an E1 reaction. And on a secondary substrate, I don't think you're going to get an SN2 reaction. If it were primary, we'd have to worry about that, but it's a secondary substrate. Because the bromine is attached to a secondary carbon. Also be aware the leaving group does not have to be a bromine. It could be a chlorine, it could be an iodine, it could be a tosylate. So don't memorize that it's Br. It's not always Br. There are other leaving groups as well. Now, in the next box, redraw compound A using wedge and dash bonds to specify the stereochemistry required to ensure that the carbon-carbon double bond forms between B and C, not between A and B. And you can see the legend over here. So that means we want the bromine to be trans to this hydrogen. Remember that to get an E2 elimination, you need anti-periplanar geometry. That's something we went over in chapter 11, and that's something I expect you to know. You need anti-periplanar geometry. But not only that, we need the bromine to be cis to this hydrogen. Because if the bromine is trans to this hydrogen, then you're going to get the double bond between A and B. So we want the bromine to be cis to this hydrogen and trans to this hydrogen. So we'll simply set up wedges and dots to make sure that that's the case. So we want the bromine to be cis to this hydrogen. Otherwise, we'll get the double bond here if they're trans. So the bromine needs to be on a dotted bond, and the hydrogen on a wedge bond. And actually, that's not the prettiest way of drawing it in the world, but it would be acceptable. And then we want the bromine to be trans to this hydrogen, because that way we'll get the double bond here. We need, again, trans-periplanar or anti-periplanar geometry. So the bond to this hydrogen needs to be a wedge bond, and the bond to the methyl group needs to be a dotted bond. So that was the answer I was looking for. Does it fit? Yes, it does fit in the box. Next, in the box provided, draw the chair conformation of compound A, showing the bromine and hydrogen in the required conformation to allow the E2 reaction above. Well, there's many correct ways of drawing this chair. But we need to make sure that the hydrogen and the bromine are both axial. That's another thing you'll need to know. The hydrogen and the leaving group have to be axial, one pointing up and one pointing down, in order for the E2 reaction to happen. That's something we went over in class, and we gave examples. So if I want the bromine to be down and the hydrogen to be up, maybe I'll put my bromine over here. And the hydrogen up. This is not the only correct way to draw it. Then my methyl group is down. And I have a hydrogen up over here. Using the same numbering system, A, B, and C, carbon B over here. This is carbon C over here. It has the hydrogen up and the methyl group down. This is carbon B over here. It is the bromine down and the hydrogen up. And then on the next carbon over, we have the phenyl group up and the hydrogen down. Because the phenyl group's on a wedge bond, the hydrogen is on a dot bond. Oops. And that's carbon A over here. So that's not the only correct way to draw it. You can turn that ring any direction you like.
I had a question.
Sure.
Could the Br and H be both on axial coplanar groups, or on equatorial coplanar groups, or do they both have to be axial?
No, they have to be axial.
Okay.
In order to do the E2 reaction.
Thank you.
And one should be pointing up and one should be pointing down. In the equatorial position, you won't get the elimination. For the elimination, they have to be axial. And there's no exceptions to that. I'm trying to think if I can come up with another correct way to draw it. Oops, that's not what I meant to do. So since A, B, and C go counterclockwise, this is going to be my A carbon. This is going to be my B carbon, and this is going to be my C carbon. And on carbon C, my hydrogen is up. And my methyl group is down. On carbon B, my hydrogen is up, and my bromine is down. And then on carbon A, the phenyl group is up, and the hydrogen is down. So that's another perfectly acceptable way to draw it. Any variation on that is fine, as long as the hydrogen and the leaving group are both axial and one is up and one is down. Well, you also need it to match the drawing, right? This hydrogen is up, so that means this hydrogen must be up. The bromine's down, so the bromine has to be down on the chair form also. So all that needs to match. Next, there are two common isotopes of bromine, 79 and 81, just as there are two common isotopes of hydrogen, hydrogen 1 and deuterium. In the case where bromine 81 is present in compound A, what would we expect to be true about the rate of the reaction relative to when bromine 79 is present? Well, in class, we said that carbon-deuterium bonds are slightly stronger than carbon-hydrogen bonds. And so reactions that involve breaking a carbon-hydrogen bond would be slightly faster than the reaction breaking a carbon-deuterium bond. We would expect the same pattern to apply here. We're breaking a carbon-bromine bond. Breaking a carbon-bromine 81 bond would be a little bit slower because we'd expect that bond to be a little stronger than breaking a bond between carbon and bromine 79. So I think the best answer is that the rate would be slower for bromine 81. I think that's the best answer. Good. So yeah, you still need to know how to draw cyclohexane chairs. You might have to on this exam. This question was perfectly fair game. Now, these types of questions are very common in organic exams where you need to fill in the product. And the correct answer for full credit is always, without exception, exactly one neutral organic product. We're looking for the major organic product. That's unambiguous, the major organic product. So just like active always says, ignore inorganic side products, we'll do the same here. So here we're given a secondary bromide, and we're treating it with sodium cyanide, which remember, NaCN is Cn minus. The sodium ion doesn't play any role in the chemistry. It's just a spectator ion. And again, we're given DMSO. You need to know that's a polar aprotic solvent that favors bimolecular reactions, like SN2 and E2. So we've got a secondary substrate. You need to know that cyanide is an excellent electrophile, outstanding electrophile, nucleophile, sorry. Cyanide is an outstanding nucleophile, one of the best ones there is. So you've got a strong nucleophile, a polar aprotic solvent, and a secondary substrate. We need to come to the conclusion that this is going to be an SN2 reaction. And so that means the cyano group is going to replace the bromine. But not only that, you will get inversion of configuration. That's something you need to know about SN2 reactions. That you get 100% inversion of configuration. This carbon's not affected because there's no reaction at that carbon. But at the carbon where the reaction happens, you get 100% inversion of configuration. So that's the correct answer.
Could you repeat how you figured out it was SN2 instead of E2?
Because I know sodium cyanide is a really good electrophile. Nucleophile. I don't know what's wrong with me tonight. Nucleophile. It's not a base. Bases are things like hydroxide and F oxide and methoxide.
Oh, okay. So if it were a base, then it would be
And we would be looking at an E2. And that's actually a really good question.
S2.
What would we get if we had an E2 reaction? First of all, what would you be given? Well, we just had an E2 reaction.
A strong base.
Yes, you might be given something like sodium methoxide. And the solvent doesn't really matter once you have a strong base. You could use ethanol. Or you could use DMSO if you just want to put your thumb on the scale and make sure that you get a bimolecular reaction. But, oh, that's right. We're actually perfectly set up for it. Our hydrogen over here is trans to the bromine. So I would expect to get the double bond here. And the ethyl group over there. That would be an E2 reaction. Now you'll notice I took away the wedge bond from the ethyl group and made it a bond that's in the plane. That's because alkenes are planar. They're sp2 hybridized at these two carbons. So I would expect you to know that. If someone had left that as a wedge bond, it would lose points. Well, maybe a point, I don't know. But it would not be perfectly correct. It shows that the student doesn't understand about the geometry of an alkene. So it would not get full points.
I have a question. Is the ETOH the strong base in that situation?
Remember, ET stands for CH3CH2.
Okay.
So no, the strong base is the
This is
sodium
the Na.
oxide.
Okay, and then the sodium methoxide will be the one, like in the mechanism.
Right. Well, in the mechanism, you would just use ETO minus.
Yeah, ETO minus, because the Na is a spectator.
Right. So what would the mechanism look like? I don't know if this will let me put lone pairs on it. Oh, it will. So you'll notice I don't even show the sodium. It's irrelevant. It's a spectator ion. And the ethoxide ion would pick off the proton, form the double bond, and lose the leaving group all at once. Oh, is that too confusing? Let me draw the other arrow this way. That might be a little easier to see. So this arrow means the ethoxide picks up the proton and becomes ethanol. This arrow means the electrons in the CH bond are going in between these two carbons and making a double bond. And this arrow means that we're breaking the carbon-bromine bond and losing bromide as a leaving group. And you get this as the product. So that's what we would need to get an E2 reaction.
So just to reiterate, there's no dash or wedge on the CH2, CH3 because it's an alkene and there's nothing else attached to it.
Right, well, because it's an alkene, that's the only reason.
Okay.
Alkenes are flat, they're planar.
Okay, gotcha.
And so that whole portion of the molecule Let's see if I can manage this. Kind of failing at this. I'm trying to show that this whole portion of the molecule, this carbon here, this hydrogen here, this carbon here, and this carbon here, as well as the two alkene carbons, all lie in the same plane. So if the question had been this instead, with sodium ethoxide and ethanol, this would be the answer. Since instead of a strong base, you have a strong nucleophile, let me get it right this time. And I expect you to recognize cyanide ion as a strong nucleophile. Another one is azide. We went over both of those in class and their structures. But since it's a strong nucleophile, we expect that to be an SN2 reaction. All right. In the next one, we're given a tertiary substrate. That carbon is tertiary. Remember, tosylate is a really good leaving group. For you guys, I would write this as OTOS because that's how it's done in your book. I forgot to do that here. I'm used to using TS and not TOS. So that's what that means. It means tosylate. But in case I forget, TOS and TS are the same thing. They both mean tosylate. And we're treating it with a protic solvent. I would expect you to recognize what CH3CO2H means. It means acetic acid. C double bond O, OH. That's what CH3CO2H means. So we're treating it with a protic solvent and heating it. And there's nothing else present. Also, we have a tertiary substrate. Tertiary substrates like to make carbocations because tertiary carbocations are the most stable carbocations. So the only question is, will we get, well, we're going to get a unimolecular reaction, either SN1 or E1. And in fact, under the circumstances, I'm sure I accepted both. So the way you know what to attach for the SN1 reaction is you attach everything except the H. The H is going to go away over the course of the reaction. And so this oxygen will wind up being attached where the tosylate is. So that's the SN1 product. And there's no stereochemistry because that carbon is not chiral. The other possibility is to get the E2 product. Or E1 product. And under the circumstances, I'm sure I accepted both. I try my best not to write questions with two correct answers. But every once in a while, I mess up. So I think both those answers are correct. Good.
I had a question about the
Sure.
once the main group
I can't,
Oh, sorry. Once the leaving group leaves and the
Right.
carbocation is created, so you said the hydrogen is the part that attaches? I was just confused about where the acetic acid attaches from, like
it
how it
attaches
does it.
from this oxygen.
Okay.
We'll go over the mechanism after I finish these two.
Okay, thank you.
So for this one, we're adding HCl across an alkene. That should be a very familiar reaction. Markovnikov's rule says the chlorine is going to be attached to the more substituted carbon and the hydrogen to the less substituted carbon, because you're going to, ooh, wrong ring. Because you're going to get the most stable possible carbocation. Oops, that's no good. So the carbon in the methyl group is this carbon in the CH2. We can go over that mechanism too if we need to. But this is just electrophilic addition of HCl across a double bond. And the next question is like it. And I think that one will make more sense also if I go over the mechanism. So the first step of the mechanism is breaking the bond between the carbon and the tosylate. And you get this tertiary carbocation. And in the next step, the acetic acid attacks. So it attacks from that oxygen. Actually, it could attack from the other one too. Yeah, it really could. Actually, I know what a better answer is. So you get this intermediate, and now we just need something to pull that proton off. Let me fit it over here, actually. I have to be honest, this is actually a bit of a lie, but it's the way I want you to learn it, because that way it'll be consistent. We can worry more about the details of acetic acid next term and how it behaves. But an acetic acid molecule or an acetate ion will pull that proton off. So what you need to know is that the SN1 reaction starts with loss of the leaving group. You get a carbocation. Then you get attack of the protic solvent, you get a protonated species. Then you use another molecule of the protonated solvent to pull the proton off the oxygen with the plus charge. And you get your final product that way. The actual SN1 reaction takes 2 steps, but there's a third step that's just a proton transfer step. That's the way I want you to learn it, and that's the way we did it in class. This is completely consistent with what we did in class, same as if we'd used water or ethanol or methanol. Does that clear up that mechanism?
Yes, thank you.
Okay. And I won't go over this mechanism because we've done it a million times. This mechanism, though, I will go over. First, I'll show you the answer. We're going to get addition of HBr across that double bond. You'll get the more substituted secondary carbocation. So you'll get the bromine here and the hydrogen on this carbon. Or will you? This relates to what we talked about in class today about carbocation rearrangements. So this is the structure that's in the answer key.
Oh yeah, I had a question about that one. Shouldn't it be on the one more left to make it a tertiary?
It absolutely should be. Again, I'm sure I accepted both answers because this is going to undergo a carbocation rearrangement. So we'll go over that mechanism. And remember, problems like this don't ask you for the mechanism. It just says draw the product. So it even says you do not have to show the mechanisms. So we've got a plus charge on that carbon. And the bromide could just attack there. But another potential pathway is to do a 1,2 hydride shift, like we talked about in class today. So that hydrogen moves over, gets rid of the plus charge by taking the electron pair with it. And you get a tertiary carbocation. This carbon is now a CH2. One of those H's was there to begin with. The other one moved over from next door. So this is a 1,2 hydride shift. And then bromide attacks. And that's how you get this product. So again, under the circumstances, I'm sure I accept both. I actually think this answer is a little more correct. In the answer key, I just have this, but I'm sure I accepted both answers. And again, I don't like writing questions like this that have two correct answers, but every once in a while I mess up. Good. Now we come to mechanisms. And there are going to be mechanism questions on pretty much every exam from now on also, all the way through Organic 2. Well, actually, there might not be, since they've changed the order of chapters in that one also. I don't know if there'll be any mechanisms on the fourth exam. But first of all, we have to figure out what type of reaction this is. We have a tertiary substrate. We're treating it with a protic solvent, and we're just heating it. There's no nucleophile or base present. But we also are given the product. So remember, in mechanism problems, always look at the product and see what changes have taken place. Here, we've changed the tosylate for ethoxy. And the ethoxy needs to come from the ethanol. So it's a substitution reaction. And since it's a tertiary substrate, our substitution reaction needs to be unimolecular. This is going to go through a tertiary carbocation. So this is going to be an SN1 reaction. And the first step in both SN1 and E1 is loss of that leaving group. And that's going to leave us with a carbocation. In this case, a tertiary carbocation. And you'll notice I've done it again. I've changed the methyl on a dotted bond to a methyl with an in the plane bond. That's because carbocations are also sp2 hybridized, so they are planar. So yes, if someone had left that as a dotted bond, that would probably have lost a point. It's not entirely correct. It shows me that the student doesn't entirely understand about the hybridization of carbocations and is just copying it. You have to be thinking about what's going on. So you get this carbocation. And then remember, the first step, you lose the leaving group. In the second step, your protic solvent attacks. And it's going to attack from whichever atom has the lone pairs on it. In this case, it's the oxygen. So that's going to attack your carbocation. My phone is blowing up. I don't know why. No one texts me all day long. And then when I'm giving a review session, everyone has to text me. I guess that's the nature of cell phones. So you get this intermediate. Oh, I still have a lone pair on oxygen. I would say you need to show lone pairs on every atom that doesn't have a zero formal charge or has some unusual kind of bonding situation. So step 1, lose the leaving group. Step 2, the Protic solvent attacks. And you get something that looks like the product, but it is an extra proton on it. That's the end of the SN1 reaction. But we need to lose that proton in order to go to a neutral product, in order to go to the product that you're given. So you use a molecule of the Protic solvent in order to do that. Just like we did a moment ago with acetic acid. And once we remove that proton, that gets rid of the plus charge in oxygen, and you have your product. So that's the mechanism I was looking for. I'm just going to take a quick bathroom break, and I'll be right back. All right. What about the next one? In the next one, we're given a primary substrate and treating it with a strong base. So I would expect you to recognize ETO minus as a strong base. And we get an alkene. So some kind of elimination reaction has happened. There's a carbon-carbon double bond here that we didn't have before. And so we're going to get an elimination reaction. The question is whether it's E2, E1, or E1CB. Well, it's not going to be E1CB because I see no way to get a stabilized carbanion, and because bromide is a pretty good leaving group. You usually want a pretty bad leaving group for an E1CB and a stabilized carbanion. So it's not E1CB. It's not going to be E1 because our substrate is primary, and primary substrates prefer to act by bimolecular reactions. So this is going to be an E2 reaction. And the correct mechanism for an E2 reaction has the base pulling off the beta proton, base is erythoxide. That's going to pull off the proton. This arrow means that the oxygen reaches out with its lone pair and forms a bond to the hydrogen. Then we need to break that carbon-hydrogen bond and put the electrons in between the two carbons to form a double bond. And then we need to break the carbon-bromine bond, otherwise carbon has 5 bonds, which is bad. So that's it. The E2 reaction and SN2 reaction have one step. Everything happens all at the same time. So if you try to show an E2 or SN2 reaction in multiple steps, it's wrong. It all happens in one step. And that answer would receive full credit. I get asked a lot if you can draw on the structures that you're given or if you always have to redraw it. You can draw on the structure you're given if there's a way to do it and be unambiguous about where everything is. If you're not sure about it, if you're not confident about it, then redraw the starting material molecule. That's the best advice I can give you. But it's all one step. So those are 5 reactions you will need to know the mechanisms of: SN1, SN2, E1, E2, and E1CB. You'll need to recognize those reactions when you see them and know the mechanism if you're asked. And don't just memorize the examples from class. I can almost guarantee you the examples from class are not in the exam. You need to be able to apply the information to a similar situation, similar but not identical. That's a very important skill to learn. Very important in upper level classes, very important in medical school, very important in graduate school, to be able to apply information to a different but similar situation. Good, that's enough of that sermon. Oh, there's another mechanism. So here we're treating a secondary alcohol with H3O plus. Remember that H3O plus, we said this in class today, H3O plus implies that H2O is also present. H3O plus means a dilute acid solution. And we get a double bond, which means an elimination has happened. But the double bond isn't connected to the carbon that has the OH on it. The double bond is between these two carbons. So that means some kind of carbocation rearrangement has happened. So we're going to get an elimination reaction, elimination of water, and formation of a double bond, but there's been a carbocation rearrangement. So this is an E1 reaction with carbocation rearrangement. So the first thing we need to do since OH is a terrible leaving group, we need to put a proton onto that oxygen. And the only thing we have available to do that is H3O plus. So there's our H3O plus molecule. In the first step, you'll show the oxygen being protonated by the hydronium ion. And now we have a water molecule as a leaving group. Water is a very good leaving group, unlike OH. So in the next step, we lose the leaving group. That's always going to be the case in a unimolecular reaction, E1 or SN1. And we're left with the secondary carbocation. This can now rearrange. It undergoes a 1,2 hydride shift. The hydrogen moves with its electron pair from next door over to that carbon. That's another 1,2 hydride shift. And we're left with a tertiary carbocation. That means this carbon is now a CH2. One of those two hydrogens was there to begin with. The other one just moved over from next door. So now we have a tertiary carbocation, and all we need to do to complete the E1 reaction is lose a beta proton. So always go over one carbon away from where the carbocation is. Always, no exceptions, to pull off a proton. And now all we need to do is figure out what to use to pull the proton off. Well, again, H3O plus implies that H2O is present. So that's what we'll use. That's going to be our base. We can't use OH minus because we're not given OH minus. I don't see NaOH or something like that mentioned. So I can't use OH minus. It doesn't make sense to use OH minus anyway, since we're in an acidic medium. So we'll use a water molecule. Water will pull off this proton. The electrons in the carbon-hydrogen bond will go in between the two carbons and form the pi bond. And that gives you the product. Now, this was a hard question, I will admit, but I don't think it's unreasonable. I think it's a completely fair question given what we've learned about the E1 reaction and about carbocation rearrangements. I do wish I'd also put H2O as well as H3O plus. But it's a perfectly fair question. Good. Any questions on any of those steps?
Just curious, why is hydroxide a bad leaving group?
Because hydroxide is a very strong base and it doesn't stabilize the minus charge on oxygen very well. Unlike bromide, which is a very weak base. So the stronger the base, the worse the leaving group.
Okay, thank you.
Yep. So what's happening here? Looks like we're doing an addition reaction of water. This is a hydration of the double bond, like we talked about today in class, but there's also a rearrangement in here. So I would say this is a hydration of double bond. With a carbocation rearrangement. And you can see the rearrangement. The carbocation's here and then it's over here. So in the first step, the double bond shifts out in this direction and picks up the proton from H3O plus. And leaves a water molecule behind. That gives us this carbocation. And then we got to get from this carbocation to this carbocation. It looks like a methyl group has moved over. This carbon has two methyl groups here and only one methyl group here. This carbon has no methyl groups here and one methyl group over here. So one of the methyl groups is moved over. To go from a secondary carbocation to a tertiary carbocation, which is much more stable. Then, when we look at the change that's taken place, it looks like the oxygen of water has gotten attached to the carbon where the carbocation is. So that means water is going to act as our nucleophile and attack the carbocation. This is what we said today in class. Water acts as a nucleophile and attacks the carbocation. And you get this intermediate with the plus charge in oxygen. And now all we need to do is lose a proton on that oxygen, and that gets rid of the plus charge. And as we said today in class, we do that using a water molecule. That pulls off the proton, breaks the oxygen-hydrogen bond, pushes the electrons onto oxygen, and gets rid of the plus charge, and gets you the product. So that's the mechanism I was looking for. Those 1, 2, 3, 4, 5, 6 arrows. How did I know it was hydration of the carbon-carbon double bond? Because I see the double bond is gone and I see an OH in the product that wasn't there before. That means we've added HOH across the double bond. And how did I know there was a carbocation rearrangement? Because we were basically shown it right here, that it goes from a secondary carbocation to a tertiary carbocation. I also know it because the OH winds up being attached to a carbon that's not involved in the original double bond. So somehow my carbocation has moved. And remember, when a carbocation rearranges, we never use arrows to show the plus charge moves. That's always wrong, always, no exception. Instead, we use an arrow to show what has shifted over to get rid of the plus charge. Usually a hydrogen. In this case, it's a methyl group. That's about all I can think of to say about that.
Just real quick, do you have to write a statement of what's happening in the mechanism?
Only if it says to. I'm
Okay.
just doing it for clarification.
All right. And also, could you say that this was an addition reaction of H3O plus?
I would say addition of H2O.
Oh, right, yeah.
And yes, you could say that too. Hydration means addition of H2O.
Okay, gotcha.
I'm just writing these down so that on the video, people can see what kind of reaction it is.
Yeah, makes sense.
Good. And then over here, we need to figure out what kind of reaction each of these is. So here you do need to say what type of reaction. The answer for each of them is going to be either SN1, SN2, E1, E2, or E1CV. In the first reaction, we've got a primary substrate with a really good nucleophile and a polar aprotic solvent. And when we look and see what's happened, we see that the tosylate has been replaced by the cyanide. So that's a substitution reaction. That means it needs to be either SN1 or SN2. And since we have a primary substrate and a polar aprotic solvent, we're not going to get a unimolecular reaction. We're going to get a bimolecular reaction. So this requires recognizing that CN- is a really good nucleophile, recognizing the polar aprotic solvent. DMSO is not the only one. There are others. I could have put DMF, I could have put THF, I could have put acetone, I could have put acetonitrile, I could have put diethyl ether, I could have put any polar aprotic solvent. So DMSO is not the only one you need to know. But since we're replacing the tosylate with the cyano group, and since we've got a primary substrate and a polar aprotic solvent, I think SN2 is the best answer. In the next problem, we're treating a tertiary substrate with a protic solvent and heating it. And there's nothing else, no base, no nucleophile apart from the solvent. And when we look and see what has happened, we see that the bromine has been replaced by methoxy. That methoxy must have come from the methanol. So we've again done a substitution. We've substituted the bromine for the methoxy. And that if it's a substitution, that means it's either SN2 or SN1. Since we have a tertiary substrate and a protic solvent, I would expect you to conclude that this is an SN1 reaction and goes through a carbocation. In the next one, we have a secondary substrate, so we don't get much help from that. Secondary substrates can go either unimolecular or bimolecular. But we're treating it with a strong base in a polar aprotic solvent, and we get a new double bond that wasn't there before. New double bond that wasn't there before means we have an elimination reaction. So this must be either E1, E2, or E1CV. The way we know which it is in this case is by looking at the solvent. Acetone is a polar aprotic solvent like DMSO. And that's not going to support carbocations. You can't have a carbocation in a polar aprotic solvent. Polar aprotic solvents aren't able to stabilize carbocations. They're just too small in order to do that. So since it's an elimination reaction and we're not going through a carbocation, this must be an E2 reaction. over here, we're given the same starting material in a polar aprotic solvent, DNSO. That means it has to be either E2 or SN2. And it looks like we're replacing the tosylate with this whole big thing here. Can you see how this and this are the same thing? So we've done a substitution reaction. We've substituted the tosylate for this group with a 5-membered ring. And since we're in a polar aprotic solvent, we're not going to get a carbocation. So of the two choices, SN2 and SN1, this must be an SN2 reaction. In the next one, we're given a tertiary substrate. So that means it's going to prefer to get a carbocation if we can get one. All we're given is a protic solvent. There's no nucleophile and no base to speak of. And I see a double bond in the product that wasn't there in the beginning. A new double bond means we have an elimination reaction. So that means it must be E1, E2, or E1CB. Since we're in a protic solvent that's also acidic, E1CB reactions require a strong base. And since the solvent's protic, we're not going to have an E2 reaction, probably. Especially not since we have a tertiary substrate. A tertiary substrate is going to want to make a carbocation. So this is going to want to go through the two-step type of elimination through the carbocation. In other words, it's an E1 reaction. And the way you know that is partly from the solvent, partly from the substrate. And partly because we see a double bond where there wasn't one to begin with. And finally, in the last one, we're given a compound this is going to require a bit more explanation. So in the last one, we're given a compound that has a not so great leaving group. There are beta hydrogens over here, plus 2 more over here that are equivalent. No, I lied. It's just these two. And we're given a strong base. NaNH2 means NH2 minus. So that's the conjugate base of ammonia. It's a very strong base. The way I know that is because nitrogen doesn't very well stabilize that minus charge. Yes, it's a little electronegative, but it doesn't stabilize the minus charge very well. So I expect you to recognize NH2 minus as a strong base. And in class, we said if you're given a substrate that has a poor leaving group with a really strong base, and you see a new double bond being formed, this is an elimination reaction. But since we've got a strong base and a poor leaving group, this is going to be an E1CB reaction. And the mechanism goes by, you're not asked for the mechanism, I'm just showing it for clarity. The mechanism goes by deprotonation. And formation of a carbanion intermediate. Crap, that looks absolutely horrible. But there's a minus charge and a lone pair on that carbon. Oh, and there's still a hydrogen over here. There, now you can see the minus charge in the lone pair. And then in the second step, the lone pair in the carbon goes in between the two carbons to make a double bond. And we break the carbon-chlorine bond. We lose that poor leaving group. Well, and you get this. So that's an example of an E1CB reaction. What you need to know is an E1CB reaction is going to happen when you have a strong base and a poor leaving group. And in this case, we also get a well-stabilized carbanion, because the carbanion is stabilized by resonance. There's another resonance form. That looks like this. So strong base, poor leaving group, stabilized carbanion. That's when you'll get an E1CB reaction.
Again, just curious, but what makes the HCl a poor leaving group? The chloride.
Well, it's poor compared to bromide and iodide. It's not terrible, but it's not great either.
Oh, okay.
Terrible would be fluoride or hydroxide. So structures corresponding to those names. First, Z2-methyl-3-hexene. One, two, three hexene. Two methyl, 1, 2, 3, 4, 5, 6. Actually, I could even have 1, 2, 3, 4, 5, 6. Yes. So Z meaning that the two groups that are of higher priority are on the same side of the double bond. And I think I could even have called that trans 2-methyl-3-hexene, since there are still two hydrogens attached over here. So cis and trans still work. 1, 2, 3. I'm just double checking myself. Yes. And then 2-chloro-3-ethyl, 1-cyclopentene. So we put an ethyl and carbon 3. And a chlorine and carbon 2. Yeah, I think that's correct. And finally, we're to find the degree of unsaturation or index of hydrogen deficiency from those formulas. It doesn't say to draw examples of the compounds, so we don't have to. We just need to find the degree of unsaturation. So C6H8Br2O is the same as C6H8Br2. The oxygen is no effect on the degree of unsaturation. And that's the same as C6H10, because halogens replace hydrogens. So with 6 carbons, if the compound were fully saturated, it would be C6H14. The degree of unsaturation is 14 minus 10, which is 4, divided by 2 is 2. That's using the same formula we gave in class. Since there's 2 sets of 2 hydrogens that are taken away, its degree of unsaturation is 2. That means there's 2 pi bonds, a pi bond and a ring, or 2 rings. C11H26N2. Remember that for every nitrogen, we have to throw out a hydrogen with it. So that's going to be the same as C11H24, because you throw out NH for every nitrogen, because nitrogen is 3 bonds rather than 2. So each nitrogen brings in an extra hydrogen with it. So C11H24 with 11 carbons, CnH2n plus 2. 2 times 11 is 22, plus 2 more is 24. So this compound is already fully saturated. So using the formula, it's 24 minus 24 is 0. 0 divided by 2 is 0. So that compound is fully saturated. Let me actually write that over here also. 10 minus 6 divided by 2 equals 2. (24 minus 24 divided by 2 equals 0. And this formula over here, C14H16, has the same degree of unsaturation as C14H16. Oh, C14H16O2 is the same as C14H16. So that's a very unsaturated compound. If it were fully saturated, 14 times 2 is 28, plus 2 more. Remember, 2n plus 2, twice the number of carbons plus 2 more. 2 times 14 is 28, plus 2 more is 30. So the degree of saturation is that maximum number of hydrogens, which is 30, minus the number of hydrogens you actually have in the molecule, which is 16, divided by 2. 30 minus 16 is 14, divided by 2 equals 7. So that's the answer. And that's pretty much it. As usual, I'm not going to say exactly what's on the exam, but all of these questions could have been. They all were fair game. So it's on chapters 7 and 11. And my cat is scratching at my door. He hears his human's voice. Poor kitty. Now he started meowing. Anyway, any other questions?
No, thank you so much.
Sure.
I don't have any more questions. I just need to practice.
Yup. Practice is the main thing. Good. Well, then I guess I'll see you both on Monday.
Yep. Thank you, Professor. Have a
Try to
good
get,
afternoon.
yeah, no problem. I'll try to get this up on YouTube by tomorrow morning. I'll do my best.
Sounds good. Have a good one.
Yup, you too.